Hello everybody and welcome to Lean Day 6. Today we're going to be talking about some implications using propositions, and hopefully that'll slide us into functions, which I'll probably do next time because I don't have much time today. Anyway, so I've already started writing some things out here. So if we have two propositions, P and Q, we could make a different proposition that P implies Q. So here's some examples. So for our first one, if it's raining, then the streets are wet. Now sure, there are like some arguments to be made, like what if it's under a bridge, right? And maybe that part of the street's not wet, but in general, if it's raining, then the streets are wet. Our second one we've got is that it's raining, so that's all we have for that one. And so basically, we're gonna try to put this into Lean. All right, so we have two propositions, P and Q, and we have a proof of P to Q, and that's P implies Q. We read this as P implies Q, and we have a proof of P. And what we're gonna get out of this is a proof of Q. Let me slide this over so it's in the middle. And we're gonna call that arrow elem. So what does this allow us to do, right? This basically allows us to conclude that if it's raining, then the streets are wet. So when we have our second premise, it's raining, we can jump up to our first premise that if it's raining, then the streets are wet, and we know that the streets are wet, right? Now, on the other hand, what if it's not raining? Can we conclude anything? Now you might be thinking, if it's not raining, then the streets are probably dry, right? Well, what if it had just stopped raining? What can we conclude then? Are the streets instantly dry, or are they still wet? Well, our implication only allows us to go in this direction. That if it's raining, then the streets are wet. We can't just go, all right, but maybe the streets are wet, so it must be raining. Like that doesn't really work, right? I could just pour water on the road. It's like, oh, it's raining now. That's just so weird, right? So we can only go in the direction that we define. So how can we turn this part into Lean, right? So what do we need again? We need a definition. We're gonna name it. We're gonna call this one arrow elem because that's what I decided to name it over here. And then we have our two propositions, P, Q. They are propositions. And we need our proofs. So we're gonna use this proof, which is basically this first statement here, and our second proof, which is this one right here. So you can substitute those into your mind. So we have a proof of P to a proof of Q. And we're just going to put the exact same thing in here. If you want to get this little arrow, you do \R. There's a lot of things you can do. You can read it right here, \R. I don't really use just the arrow one because it doesn't convert it. I think we do that. Yeah, it doesn't convert it. I don't like that. Let's see what else we got. \R dash, \imp, so that just implies. That makes sense, right? I wouldn't do \right arrow or \long right arrow. That's just completely unnecessary. I mean, you could do it, but I don't know why you would. So proposition of P implies Q. And our last proof of P. All right. So we are input and our proofs. And that's going to, and we want Q out of this. And we have our bind, and right now we're using sorry as usual. We don't want to do that, so we need to fill this in. Now we've basically given ourselves the tools to do this right here. So we can reread this. If it's raining, And if it's raining, actually, oops. Let's re-say that. Let's rephrase this. It's raining, and we can use this since it's raining. So basically, this is pretty much like a function. It takes in a proof and outputs another proof. So let's use our proof, p to proof of q, and we need to input our proof right here, right? It's not gonna really make sense if we just input a proposition, because that proposition can be like anything, right? So we're gonna input the proof, and so our proof of p is true. We're just gonna assume that. And this takes that true proof of p and outputs a proof of q. And that's what we want right here. So we can go ahead and check this. And as we can see, it pretty much worked. So hopefully it sticks. So the first part in parentheses is our proof of p to proof of q. And that means that when we have our proof of p, which is that second M1, we'll get a proof of q, basically q, which is that M2. All right. So that's basically just our new arrow rule. So let's keep going along with this. What if we wanted to prove like the not version? All right. So we could also do, let's make a comment. P and Q are propositions. We have a proof of P to Q, and that is P implies Q. And we have our proof of not Q. So not is just backslash not and then Q. Draw some lines in here. And what are we going to get out of this? We're looking for proof of not P. Not P. Now this is like modus tollens. Probably butchered that one as well. Let's just call it that because it'll be easier. And this basically is flipping it. So we know that if we have P implies Q, that doesn't necessarily mean that Q implies P. But what you could do is basically not Q implies not P. So if the streets are not wet, then it is not raining. Does that sort of make sense? If the streets are not wet, then it is not raining. See, that still works. Because once it starts raining, then the streets are wet. So you can go the opposite way around, but only if they're not. And that's basically just a proof of contradiction. I don't know if I want to do it now or I want to do it later though. Let's do it later. We'll talk about negation later. I want to get through more of the implication. So let's talk about let's just use a bit more variables in this for implications. So let's define some variables. We're going to define two. We have P and Q, and remember those are going to be our propositions. Oops. I always hit enter because I think it's going to work. And then it just gives me that. It's great. Oh my gosh. Okay, and we're gonna have another variable. We're gonna call this implies, and that's gonna be p to q. Oh, to q. Now, variable's been kind of dangerous because you might accidentally make a variable that works like an axiom, and you don't want to make axioms, especially when they're wrong. And I'll do an example of that in a moment. And well, let's have another variable. And let's just call that our proof of p is p. And so when we go ahead, oh, and it gave me pi. Wow, it's giving me so many fun things. Let's just go ahead and check. And we're going to use implies proof of p. And we can see that the proof of p, well, implies proof of p gives us q. And that's pretty much what we did up here, just in some variables. Now, again, like what I mentioned before, we have to be very careful. Because what if we had a variable that was false implies true? All right, and we're gonna say that true just literally implies false. Oh my gosh. Just love lean sometimes. So let's make a short theorem. And let's just say that 0 equals 1. And classical logic would say that that is incorrect. If you were like, if you told a mathematician that 0 equals 1, like, they would just probably yell at you, because that makes no sense. Even like a 5th grader would be like, what? World's gonna start imploding on itself. Anyway, so let's use our false implies true. We used a false elimination here. Basically just proves false. Oh. And we're going to use our previous variable, which is the true implies false. So, I mean, false implies true. So false implies true. And true dot intro, because we're going to introduce, this is basically just true. You can see that there. So what are we doing here? We are taking this. We're inputting basically a true proposition right here. It's giving us false. False elimination is basically going to help us prove false. And suddenly, this works. And you're like, that doesn't make any sense. It's like when we discussed axioms for a moment before, I don't remember which day that was, and we just prove absurd things. So we definitely should not be doing that. So when we check it, we have that 0 equals 1, and that's not what we want. So always be careful. Always be careful with those things. So we're going to look at what we can imply with true and false. Open up common area. So which of these following implications can we prove? So can we prove that true implies true? So if true is true, then true is true, right? Our second one is going to be true implies false. We're going to have the reverse of that, false implies true. And then false implies false. All right? And we can already, like, from what we have over here, we can already make good assumptions about those just using our intuition. but we're going to go through pretty much all of these regardless, just so we can prove them out. So let's start with, I'm going to just do this in all caps, like a heading. So let's do true implies true first. So let's make a definition. True implies true. And we need a proof, because you can't just make this stuff up out of thin air. We're going to have a proof of true, and that's going to be true. It's a proposition, right? We've done this before. Basically, this right here was a proof. This is a proposition. It's not really changing anything like that. And that's going to be true. Right now it uses sorry, so let's use our bind. And we can just straight on use this proof, because we basically gave it to ourselves. So let's go ahead and check that. And we can see that true certainly does imply true, right? So that's good. So we do know that true implies true. And that should be pretty obvious, I think at least. It'd be really weird if true didn't imply true. You just have some crazy things right there. So let's move on, and we're going to talk about true implies false. So true implies false. Now, you're probably thinking, like, how do we even do this? Like, right here, we just did this right here. And, like, that didn't work at all. So actually, in order to actually even do this, because there's no way we're going to be able to have that true implies false, right? So the only way to actually prove this is to use an axiom. So if we actually wanted to prove this, just don't do this. It's cheating. Don't do it. We have a definition: true implies false. We need a proof. We're gonna just call that. Gosh. Yeah, let's do. Can I call it just proof true again? Is true. And we're getting false out of it. We need a bind. Right now it uses sorry. Yep. So the only way we can solve this is using our false elimination, which basically just allows us to use false to prove anything, and our axiom that false is proof of false, and we can actually do it. And that's just wrong on so many levels. True implies false. Suddenly we have true implies false. Just note, it doesn't work. True implies true is fine. True implies false, not okay. Alright, for our next magic act, we are going to go with false implies true. So again, let's just do the same we did last time. There we go, false implies true. Give ourselves a proof of false, proposition false, true, and the bind. So how can we do this? Well, this time we only need to say that it's true. How do we just basically get a true statement? We use true.intro. Alright, and there we go. So we do know that, actually let's go ahead and check that. That true, wait a second. right? I think it's okay. That should, I think that should be flipped. Not sure if I did that wrong, but let's just say that this does actually work. I'm gonna check my notes real quick just to make sure I've actually done this right. Alright, so let's just go ahead and actually use it. I think that'll actually work out a bit better. Let's have a theorem. Let's just do that. False implies true. Just do th for theorem. We're gonna have false implies true, and then false. What do I do? False implies true. So I have definitely messed up somewhere. Let's see what we've got. Proof of false, true, true to intro. So we have this. And then our false implies true. Alright, so this is when we're just gonna go ahead and troubleshoot the heck out of this. So here we have true implies false. This is false implies, this should be false implies true, because we basically just flipped it. Okay, maybe if we go ahead and just simplify some of this, we'll get it. So let's just have false there, false, true, true.intro. I wonder if Lee's just working correctly, because I'm pretty sure that should work. I can only copy what I have actually from the notes. Okay, so that apparently works. I've just somehow written it out incorrectly. That is very odd, actually. Okay, well, I don't know. Oh, okay, that is weird. So the check is not actually what we're putting in. That is incredibly weird. So I guess moral of the story, sometimes you can't trust Lean. Yikes. Alright, let's move on, because obviously we know that works. I'll leave this up actually, because that for some reason works. The one before, I don't know what check was doing, to be honest. If anyone actually has a clue, let me know. I would love to know. And then lastly, we need a false implies false. Let me check my time real quick. Alright, we're at about 25 minutes. That's a bit behind what I was going for. So now we need false implies false. Alright, so we need a definition. We're gonna have false implies false. We're just gonna simplify things now. Proof false we're trying to get out false, bind, and we can just use our proof as usual, right? All right. So if we want to just go ahead and use this in a theorem, we could have a theorem which is called the false implies false theorem. And we're going to say that if false, then false. And we're going to go ahead and prove that with our false implies false, which is that here. That all checks out. We can also do it with a definition. So like false implies, let's just go with 0 equals 0. Give ourselves that proof of false. We're gonna have 0 equals 1. That doesn't make any sense. That is definitely false. We'll use our false elem to show that it is false. So we have our false, proof of false, well, not proof of false. We have our false here, and we're proving that this is false. All right? And then we could make a different theorem of false, I don't know. False is 0 equals 1. So false implies 0 equals 1. Bind, and we use that really long, just false. I'm gonna just copy paste it at this point. There we go. So let's go ahead and check that theorem. All right, so if we have false, then we get 0 equals 1. We can just throw false. Oh, that's not how you spell false. So then it hates us because we're looking for a prop. But it's okay. That's what we were going for. All right, so that's basically our arrow introduction. Not nonsense. It's not nonsense. We know that true implies true. Or was that? Okay, it's all over here. True implies true. True implies false has no proof. False implies true is true. We can prove that, even though for some reason Lean was hating me. And false implies false. True implies true, and false implies false are pretty self-explanatory. You'd pretty much always assume that happens. False implies true is when sometimes this didn't quite work. It's not raining and the streets are wet, right? It could have just rained and the streets are still wet, right? But then we had the true implies false, and we knew that just totally broke down. So it's raining and the streets are not wet. That doesn't make any sense. So we have to actually use an axiom to just say that these mysteries of science could actually exist, right? So that's how we are going to do it. And that's basically our arrow elimination. So using a proof of P to get a proof of Q. I hope that helped at least somewhat at all. I am so sorry that this one was just not working out for me. I'm not totally sure what I did wrong. Again, I'm not a professional. I say that like every time. But I have it here, so this one does work. But yeah, I hope that helped. We know how to use basically our arrow now. It's just, that whole thing is basically just a proposition. But yeah, I hope you have a nice day. Thanks so much, and I'll see you next time. Take care.